Hello student, in this video I am going to discuss about how we can represent 3D objects in computer graphics. Um, 3D objects can be divided in two categories. One is boundary representation, or we can say BRAPs. It describes a 3D object as a set of surfaces that separates the object's interior from the environment. And second part is space partitioning representations. It is used to describe interior properties by partitioning the spatial region containing an object into a set of small non-overlapping contiguous solids, usually cubes. So here you can understand that in case of boundary representation, we go with the surface boundary, or we try to create a set of surfaces that separates the object's interior from the environment. And in other case, in space partitioning representations, we try to um, create a mass or a set of contiguous solids which should be non-overlapping, and try to make it small. We try to make it small and contiguous and non-overlapping cubes or cube-like structures to create that actual objects, so that it describes the all properties of the original object while we represent the object in the computer graphics or in a display concept. So if we go with the first idea, that is polygon surfaces, we can create or we design, we can project a 3D object using polygon representation. Here you can see this is an object where the surface part of this object can be represented as polygons. The most commonly used representation of for a 3D graphics objects. It is a set of surface polygons that enclose the object's interior. Here you can see these are the interior polygons, and that can it is a set of surface polygons that enclose the object interior. Set of polygons are stored for object description. This simplifies and speeds up the surface rendering and display of objects, since all surfaces can be described with the linear equation, because we can represent this plan or represent this polygon in a planar or linear equation, and that is why it can be very helpful and very speeding up process and simple one, and it simplifies and speeds up the surface rendering while we create the object or while we represent the object in the display devices, in 3D display devices. In polygon surface representation, we need three parts. First is polygon tables. Three ways to represent polygon surfaces. First is polygon tables, second is plan equation, third is polygon masses. So we'll try to go through each one of them. Here you can see in this diagram, this is the original object. Okay, this is the original object, and this has been divided in two polygons. Okay, you might divide in more than two, but try to make it we always try to minimize it so that it is helpful for us. So here you can see the vertex table, edge table, and polygon surface table need to be created while we create the polygon tables. So how we create that? Here you can see this is one polygon. So the vertex are v1, v2, v3 and v4 and v5. So vertex table is this one. So and vertex table will be like, so you can v1, for v1 there will be a coordinate. For v1 there will have a coordinate. As this is a 3D diagram, that is why there will be three values of coordinates, three axes, x, y, z. Same way v2, v3, v4, v5, all five will have a coordinate value in a 3D dimension or 3D coordinate system. And an edge table, we need to create an edge table where E1 is comprises by V1 and V2, because edge E1 is comprised by V1 and V2, or created by V1 and V2. E2 is created by V2 and V3, V2 and V3. In that way, E3, E4, E5, E6 has been tabulated here. And polygon surface table, where we have divided this whole 3D polygon in two part, S1 and S2. So S1 is comprised by these three edges, S2 is comprised by these four edges. So in this way we can represent the whole 3D polygon using these tables. So when we try to display the object, it will be helpful because we have mapped everything in this table. So just go through the map and we can draw the things, because we know that we need to, if we need to draw the polygon, we need to only draw S1 first, then S2 second, and to draw the S1 we need to know the E1, E2, E3, and to know the E1, E2, E3 we get the information from here, where vertex V1, V2, V3, V4 is here, and know the information about the V1, V2, V3 and all other vertices. We have to go to the vertex table and we'll get the coordinate values. Thus we can plot those things and we can draw the things. So this is the way to do. So object is stored by using three values: vertex table, edge table and polygon surface table. So this is the vertex table we have discussed like this, and this is the edge table, where edge is comprised of by this one, and this is the polygon surface table. Okay, polygon surface stores the number of surfaces represented in the polygon. From the following figure, surface S1 is covered by E1, E2, E3, which can be represented in the polygon surface table. S1, E2, E3, same like S2 also. And this is a plane equation, that is a second type of polygon surface representation, because we have mentioned this thing in this here, that we can do by polygon tables that we have discussed. Now we can go for polygon equation, or you can say plane equation. So we know that the plane equation for any planar surface is this one: ax, by, cz, d equal to 0, where xyz is any point on the plane, and coefficient a, b, c and d are constants describing the spatial properties of the plane. Spatial means only the coordinate properties, or you can say physical property, okay, in the 3D axis or 3D coordinate system. We can obtain the values of a, b, c and d by solving the set of three plane equation using the coordinates values of three nonlinear points in the plane. So we need to just take 3 points, x1, y1, z1 and x2, y2, z2 and x3, y3, z3. Then we need to, and those three need to be non-linear points in the plane, and we have to solve the equation to find the value of a, b, c and d. Then we can find the equation of the plane. Then we can plot any points on that same plane. So that is the procedure to use the plane's equation. We need to use 3 nonlinear points which should be in the same plane initially. Then we need to solve the equation using this equation. We have to find a, b and c and d. After we finding a, b, c, d, then we'll put that value in that equation, and for any point we can get the actual point in any part of the plane. So in that way we can draw whole plan to represent the polygon. So plane equation is this: ax, by, cz plus d equal to 0. We can obtain the values a, b, c, d by solving the set of 3 plane equation. Let us assume the 3 vertices of the plane are x1, y1, z1, x2, y2, z2, x3, y3, z3. So let us solve the following simultaneous equation for ratios a by d, b by d, c by d equal to -1. If you convert that equation, you can convert that equation by putting the values of x1, y1, z1 in this equation, x2, y2, z2 in this equation, x3, y3, z3 in this equation, and in that way, by dividing d to the whole equation in all three, we can get this equation. Now you can get the plane equation in matrix format, where a will be equal to this one, B will be equal to this one, and D will be equal to this one. If you solve this equation, you can get this thing. For any point x, y, z with parameters a, b, c and d, we can say that for any point x plus dy plus cz plus d will be not equal to 0. If not equal to 0, that means the point is not on a plane. For any point, if it is less than 0, that means the point is inside the surface. Ax by plus cz plus d greater than 0 means the point is outside the surface. So that is the plane equation concept. We need to solve the equation to, or you can use this matrix, because that can be derived using the Cramer rules to the above equation. So by using Cramer rules of the equation, solving these things in the determinants form, and putting any values of x, y, z now in this matrices, you can get the value of a, b, c, d. And after getting the a, b, c, d, you can get these points values. Ax by plus c plus d is, if it is not 0, then the point is not in the plane. If it is less than 0, then inside the surface. If it is greater than 0, then is outside the surface. So this is how we can go for the plane equation. Next one is polygon masses. 3D surfaces and solids can be represented or approximated by a set of polygon and line elements. Such surfaces called polygon masses. In polygon mass, each edge is shared by at most 2 polygons. So here you can see each edge is shared by at most 2 polygons. The set of polygons or surfaces together form the skin of the objects. So in that way, the mass of the polygons can create the skin of the objects. A triangle strip formed with the 11 triangles containing or connecting 13 vertices. So here in the original polygon or original objects has 13 vertices. So we try to create the triangular masses for the actual object by creating 11 triangles, and in every triangle any one among the edges might share maximum 2 polygons, or it might not share, like for these edges it might not share any 2 polygon, but at max any polygon or any edge will share 2 polygons. Here 2 triangles, for any edges it will share 2 triangles. So in that way we create the polygon masses to create the to form the skin of the object. So there are advantages of polygon masses. It can be used to model almost any object. We can create any object using these polygon masses. They are easy to represent as collection of vertices. They are easy to transform. They are easy to draw on computer screen. But disadvantage is that curved surfaces can only be approximately described. It is difficult to simulate some type of object like hair or liquid. So sometimes it might create not exact object for some curved like objects. If you create the polygon masses also, you might not get the exact object you need to represent. So in those scenario, you might need to go for another way to describe those things. So three-dimensional concepts, we have discussed this part, parallel projection and perspective projection, in the previous video, and we will go for this depth queuing, visible line, surface identification, surface rendering, these things. Now we have gone through this parallel projection, perspective projection in the previous topic. Now depth queuing. Hidden surfaces are not removed but displayed with different effects such as intensity, color or shadow for giving hint for third dimensional object. Obviously, while we represent the third dimensional objects, sometimes we need to give or hint of the hidden surfaces by providing shadow effect or by providing light effect or using color, so that the objects look like a 3D objects. So simplest solution is use different color intensities based on dimension of the shapes. So that can be created, or we can show the hidden surfaces of a 3D objects by using variety of color intensities based on the dimension of the shapes. Here you can see this teapot. Here we can see there might be parts of the objects which might be hidden or slightly in shadow part, and to show that thing we can use the intensity of colors so that it looks like a 3D objects. So that is about depth cueing. Depth cueing means we are trying to find out the depth of the object by using the color intensity. So depth cueing as method for indicating depth with wireframe displays is to vary the intensity of objects according to the distance from viewing position. So here important part is that we need to vary the intensity of objects according to their distance from the viewing positions, and depth cueing is applied by choosing maximum and minimum intensity values of color and a range of distance over which the intensity are to vary. So we can use a variety of intensity of colors, and which will depend upon the distance of the viewing position and with the object that is placed, which needs to be displayed on the screen. So depth cueing is a very important part in case of hidden surface or shadowing surface, or to create 3D surface more realistic. We need to go for depth cueing type concept to represent the objects in more perfect manner. Next is visible line surface identification. A simple way to identify the visible line is to highlight the visible lines or display them in a different color. So in case of 3D objects, or in case of if some parts of a object is not visible enough, or we need to make the users to show or make it visible but not visible in reality, but we need to show them using some way. So we need to create some highlighted lines in the actual representation of the objects in the display, or we can display them in a different color than the original color that is used to display the original objects. So another method is to display the non-visible line as dashed lines, or we can say highlighted lines. Here you can see the wireframe representation of the pyramid in. Here you can see this is the pyramid. Okay, so this is the actual, this part is original visible part, contains no depth information. This A part contains no depth information. B part downward from a position above the apex, so these objects shows that we are seeing the objects downward from a position, and this C objects is showing that we are seeing the objects from upward from a position below the base. So that is the information we can get only using this wireframe representation of the objects, or we can say pyramid in this example. So that is why we cannot directly say which part is visible, which part is not visible, or if we need to make the user to have the concept about the not seen part of the objects, then we need to go for visible line and surface identification approach, so that by using only this type of looking or this type of projections will create a will not create that much of knowledge about the hidden surfaces, or any non-visible lines cannot be seen or cannot be known by this type of projections. So next is surface rendering. Surface rendering method is used to generate degree of realism in a display scene. Realism is attained in displays by setting the surface intensity of the objects according to the lighting conditions in the scene and surface characteristics. Lighting conditions include the intensity and position of light sources and background illumination. Surface characteristics include degree of transparency and how rough or smooth the surface are to be. Here in this scenario also you can see To render the surface, we need to see where the light is coming from and where it is going, and also the intensity of the light, and also the illumination effect of the different objects. Here it is saying as like this: realism is attained in the displays by setting surface intensity of the objects according to lighting conditions in the scene and surface characteristics. Lighting conditions include the intensity, positions of light sources and background illumination. Surface characteristics includes degree of transparency. Some objects might be more transparent, some objects might be less transparent, and how rough or smooth the surface are to be. So here realism can be attained using surface intensity according to light conditions and surface characteristics. So lighting conditions can be like this, and surface characteristic condition can be like this. So you need to consider these things while you are going to surface rendering, because when you are going to create a realism, a degree of realism in a displayed scene. And it is very important in case of 3D viewing or 3D object display, and also in case of virtual reality also it is very important part. Here you can see this pistol has been shown in a cross-sectional view. So we can say that type of view is like exploded and cutaway views. Exploded and cutaway views of objects can be to show the internal structure and relations of the object's parts, and this type of views is very helpful in case of mechanical design, in case of vehicle design, in case of very automobile design, or any building infrastructure design, or if you are going to develop any type of software which involves in those type of scenario, then you might need to understand this topic, that is about exploded and cutaway views, where we try to show the internal structure and relationship of the object parts. An alternative to exploding an object into component parts is the cutaway view, which removes part of the visible surfaces to show the internal structure. So same type of thing, just a alternative way to understand that point, that is alternate to exploding an object into its components parts is the cutaway view, which removes part of the visible surfaces to show the internal structure. Another view is that three-dimensional and stereoscopic views. In stereoscopic views, three-dimensional views can be obtained by reflecting a raster image from a vibrating flexible mirror. The vibration of the mirror are synchronized with the display of the scene on the CRT. Stereoscopic devices represent two views of a scene, one for the left eye and another for the right eye. Here you can see stereoscopic devices present two views of a scene. It may be right view, it may be left view. So here you can see for the left view, you can see with the left part of the brain or right part of the brain, and same right eye view will recognize the right part of the brain to get the knowledge of the original image. So that is a stereoscopic view of the original objects, one for the left eye, another for the right eye. So that is what it is saying, that in stereoscopic views, three-dimensional views can be obtained by reflecting a raster image from a vibrating flexible mirror. The vibration of the mirror are synchronized with the display of the scene on the CRT, and the stereoscopic devices represent two view of a scene, one for the left eye, another for the right eye. And again, there is a 3D transformation. We have gone through this part about 3D transformation in the previous videos. So that's all in this video. I have gone through, actually these topics are like how the stereoscopic view or exploded view or alternated view, Those are I have covered in a little way to understand the basic things, and you can go for more knowledge about these things because of the time constraints, and to give you such basic idea about these things, and you can go for more understanding. And because these type of things are more used in case of 3D dimensional view, um, so try to understand these things. You can find more information in the book, also in the literatures also. So in this way I have concluded the 3D part or 3D object representation part, and also I'll try to go for curve representation in the next class. So if you have any doubt also, please let me know, or if you want to discuss or try to input something on this point, you can let me know. We'll try to meet over Google Meet and resolve the thing. Thank you.